Okay. Don't know why that happened. I mean, I do know why it happened, but I mean, I do know a root cause. This new stream. Diagnose it. All right. Sorry about that. I'm gonna rerun this with reduced loads. That works. Might have to just increase 16 millimeters. Still way too much. Is for a material? Yeah, it's so. I think it will have to be a thickness increase. That's probably going to be the. Just as a sanity check, let me make sure that it's applying 70 pounds across the entire part, not 70 pounds 3 times. I think that could be. Like this. Wait, that did change. It got better? No idea what. Should find out. Edit, pick, paste again. It should be roughly 12 mil. No, it changed. All right, so it does apply it each selection, which is actually better than I thought. So that actually makes this better. So we wanted 300 newtons. We divide it by 3, which means we get 100 newtons per. Yeah, 100 newtons per tang. We actually changed this to 100. Actually, to simplify this, I'm going to do just 1 tang for now. So we get 16. We want less than that. So it'd be awfully useful if they let you modify the part from FEA. Okay, that's pretty useful. Let's see if we can do that. Let's look at materials. We're at 1.6 millimeters right now. Actually, switching material would also help a lot. And for the record, we actually want, I think it was, we really only want 1 millimeter of deflection. So what can we scale this to? Um, uh, here. So I think we're going to need to double it. It's going to have to be like 3.18. So let's see if this will let me scale that accordingly. So we want X scale, want that at 3.18 divided by 1.6, so roughly 2. Should come in thicker. There's a break. There we go. It is thicker. Perfect. Run that mesh. Assume this is going to break the entire. Oh, it seems like it saved it. Good. Pick. Change our forces here. 100, and then let's see if the broke. It did. Remap that. Okay. So now let's run this. So a doubling should really have way more effect than you would think. So it does, and we're at about 4. Honestly, I'm okay with that. I think that's enough. We know that we can dial in this geometry with additional width if we have to, so I'm actually okay with it. I'm going to take that as a question of how thick does this actually have to be, and the answer is you kind of double it. We can quickly change this in the part, in the assembly right now. So I will actually just do that really quickly. Isolate all the affected parts. That's it. Move the bodies first. Actually, how do I want to do this? I'll do it one by one. All I'm doing is I'm counting for the increase in thickness here. This one from 1.6 to 3.2 essentially. All I'm doing is just modifying this geometry for that additional thickness. Right? It's 3.2 divided by 1.6. Yeah, 1.6. Then the hardware moves 1.6. Then finally, our part thickens up. Ta-da. And as always, if this is too stiff, I will break out the mallet. Mallet fixes all. I don't need these tapped holes anymore. Make the cutaways closer to center. Not sure I'm following. But in general, I think I know what you mean. It's just change the geometry, right? Reduce this width, I think. You're saying the distance from here to what I meant by geometry. On that note, we should actually fix this change that we made. That. 30. That's 120. That should be 150, I think, because it's 30 plus 20. Yeah. Okay. So now I'm going to just match this geometry to the surface. Same on this side. Pattern that through. Great. Corrected. All right. Now I want to get the holes in for this plate. The tapped holes, I should say. And then fix these. I think I forgot to modify these. Yeah, I forgot to fix. What were those? Fix these fixed to 60 off. Yep, that's right. This needs to get rotate 60 or 175. 180 minus 75, was that right? Oh, I'm going to pull out one of these screws just to double check. It was 180 minus 5. 60. No, it was 60. Okay. Good. And then we now want to mount those screws, or we want to tap part for these. That's going to be simple. I'm just going to slice that. Sure. Technically, these are screws because they don't have a pairing nut, but I know what you mean. Ask away. 0.5, and I think the tap size was 2.5 as well. That's good. So just sanity checking this. We actually need that 4 difference. Like, can we just cut this hole all the way through the part? No, we need this locating feature, so we actually do need. Okay. I think we're there. How do you, so the question is, in designing a part that you are going to assemble, technically it's an assembly consisting of parts, but I see what you mean. How do you select the specifications of the screw, the bolts, or the nuts? Is it from experience or calculations? Uh, the answer is both. So you kind of run through a series of questions yourself that you answer to get to the right answer. And it's more than one thing. So a long time ago, I asked uh, my manager at the time, uh, why why do you use hex bolts and why would you use socket head cap screws and why would you use flathead screw and why would you use uh, a button head screw? What's the difference? Which one do you choose?" And he said, "Yes." And I think he was just kind of messing with me. He was messing with me. What he was saying was, well, they all have their different applications. So go to the old ad library. When you're designing a structural assembly, say the steel and concrete building I'm in right now, you use a hex head screw, right? Why? Well, it turns out that these screws, these hex heads, have these little markings, and they do things like tell you, well, this is a grade 8 screw, or a grade 5, or a grade 2 bolt. And that tells you the strength. So they're super useful because it immediately signifies to the installer, hey, you have the wrong screw, or you do have the right screw, right? That's super important when you're designing and building concrete and steel structures like bridges and things that could hurt people. Another feature of hex head screws is that they're very easy to get a torque wrench on, and they're very receptive to taking a lot of torque. So, in general, when I think about when I use a hex head screw, it's okay, am I going to apply a lot of torque? Because it can take way more torque than a socket head screw can with the hex in the middle. Do I need the installer to know that they have the right screw? Because if they get it wrong, I will lose half my yield strength and the thing falls apart. These are questions I ask myself when I use a hex head screw. When I'm designing to things at the scale that I'm currently designing, i.e., on a desktop or tabletop, I don't really need hex heads because I don't really need that much torque. So the next question you might ask is, well, how do you know how much torque you need? And the answer is, well, there's that again. There's many, many ways to approach that problem. So there are rules of thumb. Like you can go to Fastenal, and they actually have a torque chart, recommended torque values for fasteners. And you just look at the chart and say, well, that's what I'm going to use, right? Well, why? Okay, well, that's a deeper problem. The answer is it depends on the application, but a lot of the time, the way you specify um, your torque is because you need to know how much preload you want, or you do know how much preload you want. And so, again, it depends, but they all have their different applications, and uh, generally design your screws and bolts. Well, I should say bolts. You don't really you do torque spec screws, but you torque spec screws in a very controlled way where you have some empirical data to um, roll back to. Anyways, let's stick with bolts. You torque spec your bolts when you know, okay, I need 1,000 pounds of preload, and that's this much torque. So let's say you're designing a frame and you know that you need 1,000 pounds of preload because you've done the requisite engineering to understand that 1,000 pounds of preload gives you a healthy factor of safety against the worst loading axially along the bolt, and it does a bunch of other things that you know you need. So if you do that, you then say, well, how do I find out my torque spec? And the answer is torque is equal to KFD. So you know your preload, which is F. You know the diameter of your screw probably, and then K is they give it to you here, but it's critical you have to test for this. Most of the time, your um, your regulating body will tell you what K is for certain applications. So if you're using AISC code to design a building, they'll tell you what your K factor should be. In general, though, they probably tell you what your preload should be too. So it just depends, but you can go test for K. But that gives you your torque value. And then you tell the installer that through your assembly drawing, and then they now know that they have to go get a torque wrench that can meet this requirement, and then they can go apply that torque. It's a long-winded way of saying it depends, but in general, it depends, and that's kind of what a typical case would look like. In my case, because I'm a big proponent of not complicating things, what I do is I make the mechanical design work from a top-down approach, the top down being, or the top being, what is the simplest way to assemble a thing? And then I work from there. 99% of the time, I actually never have to spec torque values, because I know this is a non-critical application. I know I'm going to use Loctite. I know that uh, the compression generated in, or the preload doesn't matter because of the three factors, and so I can just say, hand tight is good enough. This is actually a good time to ask this question because we just said that this needs, what is it, 70 pounds of preload. Can this actually generate 70 pounds of preload? I would have to go run the numbers. Actually, we can go do that right now. Can this generate 70 pounds of preload? Here's an example. We know that torque is equal to K F E. K is zero point 0.2 for now. Again, you have to look that up or figure it out yourself if you know. Roughly speaking, it's about, we said 100 pounds, no, 75 pounds, which is roughly 300 newtons. So that's 300. Keep my units over here. So that's unitless for 0.2 times newtons for the 300 newtons. And then diameter is 4 millimeters, right? No, these are M4s, I think. 4 millimeters, which is 0.004 meters. Look at that, Newton meters. I know I did this correctly. Torque is equal to zero point 0.2 times 300 times 0.004, which is 0.24 Newton meters. Can an M4 screw do that? I think it can. Depends on the class, yada yada. But yeah, I mean, see, M4, take 1.37 Newton meters. So we're fine. But see, this is a great example of, I should have checked that because my safety factor there is probably less than 5 or 2 or whatever. So long story short, it depends. And don't know, go with the cheapest solution. Socket head cap screws are not that expensive. Technically, the cheapest ones I think are button head or um, PAX. Here's a bit of advice though. You never ever use Phillips head screws because they are a pain. You only use them when you want to frustrate your user and you don't trust your user. Why you see them all over consumer products. Okay, so this works now, I think. Actually, real quick, I want to implement the DFM that I got back from SendCutSend. So the first thing they said was they could do this, but it's going to be really complicated for them, and it's going to just make the part expensive. So I'm going to get rid of all of these lightning features. Instead, do the bare minimum. Just just make this location feature here work. I'm going to gap that, say 4 millimeters. We're at 6.7. 4, yep. And then I'll give their radius there. Boom. Okay. That was the first bit of DFM. The second bit of DFM was that these columns actually need a flat on the backside here to help with positional accuracy on the machining process. So try that. What's the best way to do that? You know, I was actually thinking about this. I might change this entire column design anyways. But let's leave that for later. Let's not optimize before we have this thing working. How about that? Okay. Um, so now we should have a spinning pendulum here. We want to add a little cutout, I think, to keep, yeah, to add routing for this cable essentially. What is the current thickness? 6.35. You know what? I think we can do something here that is going to this much simpler. No, no. Um, we do want to look at the paper though, because paper gives us these parameters we want to mimic. This is what the actual mechanical parameters were for their version of the pendulum. So it actually would be a decent idea to try and mimic that. Keep it as close as possible to what they did. Because keeping it as similar as keeping it as close to what they did as possible is just going to increase the likelihood that we actually recreate their findings enough. So find the definition of those parameters. Here it was. Pull these out too, just to save. Both. Okay. So what was here's one that we care about. What was the distance between what was the length of the first pendulum essentially? That's one that we want to get right. I think they call that M. No, they call that. There it is. L1. We want L1, which is essentially the length of that first pendulum. And that is looks like 0.1645 meters. 0.1645. So that's 1.645. It was a point one? Point one. So that is 160. That's 164.5, right? Yeah. Yeah. 164.5. So let's do that. And I'm going to try and copy this design. I'm actually just going to mirror this and assume we'll be able to get that work. Some modification on it. We don't need that. We don't actually need the slip ring, I think, on the final axis. and we want to make sure that this distance from here, these center distances, is the right value. So we have this. And so it's going to be this. We want it to be 164.5. We actually want to move it down, whatever this, I think that's how this works. So this should be 1645 now. It's not. That math is wrong. Center distance, it is 311 something. So I want 165, no, 164.5 minus this. That's right. I want this dimension. Now it should be right. Almost. I don't know what I did wrong. 172. So 172 minus 164.5, 7.5. Down. Now it should be correct. And it is. Perfect. Change here. We'll also make a small change there. Just because the overlap is incorrect, I just want to get that right. We don't have to. We join them. Now, this link is roughly the same size as the link from the paper. Good. Now let's find the second link length, which they don't give us actually. That's right. You only care about the center mass distance. But you can eyeball it. I think it was roughly the same size. So what was, let's look at the line that they had. Yeah, they look about the same size. It actually looks a little bit longer. We'll just call it, I don't know, 175. Probably 200 actually. I don't have a really good reason other than it looks similar to what they did. Call that 200. The design. This actually, the design is going to be similar, the right word. Do you want to reduce mass? So why don't I do that first, and then we'll copy the design over for the next one. Actually, can I reduce the diameter here? Actually, absolutely, yes, I can. 70 right now. What happens if I bring that to 2 inches? That looks way more reasonable. I do want to add a sort of trough for the cable to travel through. That's details for later, though. Let's actually just get this modeled correctly. So I'm going to change the bearing design. but we don't have the fixed portion, relatively speaking. So let's see. We need to space this off a bit. Actually, just pull the bearing in. First, let's get a look at what we're. So gonna take a snapshot of this assembly real quick, so we can walk back to it if we have 10. My pisser to that. So move. I have to switch to another bearing. Make it smaller. I don't think we need that big bearing out here now. I do like keeping things simple by having the same part number. That's an argument for keeping that bearing. Inside's located here. Do we actually want that? We want to flip that. Hmm. We've got some weirdness going on with the location of the center point too. Let's fix that first. I think this is the center of the outer radius of this part is different from the center of the actual. So line that real quick. I can't do that because I just goofed it. That's all right. So this with sketch. Yeah, there it is. That just I was talking about. Translate this. We'll do the same thing for this. It's fixed. Great. Okay. Actually, I don't know why, but something is telling me I want to locate the outside, not the inside here. I think it's because it's going to collapse my axial distance a bit. What I want. The right thing to do. So I'm going to flip this orientation. Out of it. So actually not too much. This right. Actually, yeah, and we don't need the commutation. Um, all that. and actually either. We do need that on the other side though. There we go. This distance doesn't need so great. We can bring that down to. Actually, do we need to locate this? No, I think we said. You know what? I'm just going to delete that. We need to just getting the outside located first. So let's move this bearing in place. And so we're going to pick up bearing. Actually, we're going to sit it flush to this surface, and then we'll make cutouts here as required. Up a bit. Okay. Okay, good. Now we still need to open this up a bit. I want the inner ring to interfere. Okay, so now how do we locate? We actually need to inset this a bit. We need to locate it radially. We'll move this in, say, we want this to be a minimum 3 millimeter thick. This in, sit now. There we go. Now we have this bearing located. We're gonna have to, yeah, okay. So the next link we tie to the inside here. That's where we actually might want to copy this. Quite. The surface. We might actually just keep this nut detail. Might really just simplify this. And we can actually just use standard M12 nut. We don't need the through hole anymore. Not commutating. Am I using the right word? I think commutating is the word. It's a technical sense that I'm using it correctly. Whatever. The thread on this just so I should actually get that nut in there. But before we do, let's see. We need, yeah, we need something to clamp down on the outside here. So yeah, and it might be as simple as just pulling this out. Yeah, yeah. First, let's get that nut on. Might still have that. From with threads, but actually clean those out. All right, it works decently. So now the inner ring is totally located with this pendulum, and we now have to lock down the outer. I think that's just going to be a simple cup. So, um, that away from union to a new. Pretty tight here, but we can make that work. And then we're going to have this relative to that bearing. We're going to bring this down just a bit. Develop that preload like we did on the bottom bearing, 1 millimeter. And can this actually be sheet part? So 6.65 is a little bit more than the nominal thickness of the nearest sheet plate at 6. Which is, I think, okay. We can actually switch that to a 6.5. Yeah, we can switch that to 6.35. Develop a little bit more preload potentially, but we now can make this out of sheet metal. And then we need to open that up, obviously. Profile tolerance, cut out the machine is capable of, and then we have to add screws to that. But I actually want to put them on the backside and tap this, I think. If we have enough, don't. We'd have to increase the size of the pendulum a little bit. I'm okay. Yeah, I'm okay with that. Let's actually just pull. All right, so this can be much smaller because the material here isn't doing much. So we're actually going to reduce this side down to 35. and then we'll increase this side to 70. That's too much. Is it too much? Let's see. 70. Too much. 60. That should give us the clearance we need for that hardware now. And again, this one will be 60 as well. That should be fine. Let's join these. Clean this up. Some chamfers that will make it look better. Better way to draw this. We probably the best way to do that. The simultaneous chamfer thing was going to work. Some healthy radii. I think that. Now we are going to tap this plate. We need to find the midpoint between the two. So what defines that? It's actually this plate that does that. I'm actually going to draw it from the side. Happened. Wrong feature. Wrong button. Then we trim that. Then we lock that, and then we get our midpoint. Our midpoint. We're going to use M4 screws because we're using M4 screws everywhere else. Okay. So these go through here. Actually, wait, we can use the new slice feature. I think. Let's see. Love it if we could. I'm really enjoying that feature. So this tapped plate gets the smaller size hole, which is pre-drill hole size. Then the through hole is the bigger one. Then we delete those bodies. Okay. And then we need screws. Why did you break? You didn't break, you just didn't do it. There we go. So these thread into this plate, which doesn't yet capture this. So we need to fix that. Wait, is that right? Okay. Sorry. I now remember. This there's one more part here, and this actually joins here. So I remember. So we're actually going to move this up a bit. Be in line with the interface of that bearing. Then we bring this up to actually same deal, but it's going to be different. We're going to give ourselves that gap there now. We're going to bring this back millimeter. And then now this is going to be, let's just make it 3.18 again. Good for that flexion on the other bearing. We'll slice this. Okay, now this works. Almost. Wait, we have to pick up the outer ring there, so hide this real quick. This goes down to 30. Yeah. So that's actually going to gap a bit. And we're okay with that. It's too thick. 3.1. Now you can see the gap. That works. That is 27.8, so we'll make this 27. So now these screws will reach out to the plate. Will thread into that plate. Now the question becomes, can we get M4 screws that exact length? Because if they're too long, they will interfere with the pendulums. We actually need that to be pretty spot on. So I think it was 18 millimeters, so we want 18. Yeah. And they seem to. Are they super expensive? Not super expensive. Perfect. So we can get 18. Double check their size and then change. So they're currently whatever that is. Let's make this change. It's taking a lot of time. 18. Boom. Okay. Almost done. Question becomes, does this actually... Okay, so outer ring's located, perfect. Inner ring. Inner ring, yes. I think that's it. So we are pretty much done. We just have a little bit more to do here for this ballast. We actually do want to add a ballast here. Oh, and we want to increase this length. So I think we were at 175 before, and we said we were going to do, we were at 165 before, we said we are going to do 200. So got this. 200 minus whatever that. This should now be 200. And then we also want to come down to this size that we had. So I think was 30, 35. Come down to 35 over here as well. I just want to copy this geometry. Really direct model this. So I have to just draw it. Close enough. We delete that. So if we make that small enough, actually flip this hardware and not have tapped holes for a preload, which would be better, I think. That'll work. Yeah, I like that. No, we still have this issue when it rotates though. So, okay. And then this will be ballast, hole for a ballast. Will probably be a stack up of stainless steel plates. I know I can get in half. There we go. A rotary dual inverted pendulum. I think that's it. So I have to go do all the DFM, and then we have to do thickness. Got some that. Oh, actually, here if I pick it up before. Then 4 screws. Sleeve. Actually, the easiest way to do it is center right. Where's she located? Okay. And we'll pull this hole through. Have to pull. Six more. Yeah, what? Six there. Oh, it's what the motor was using. What's going on with that? Get this hardware roughly sized correctly. Almost there. right? I have an interface there. So we'll just pull it out. We're fine. We just have to make sure that we. Fine. I'm gonna fix that. All this is gonna come out 10 millimeters. That way, go to together. You don't have to fight with that wrench. You could countersink, but I'd like to. Countersinking is. I do it only when absolutely necessary. Kind of my rule. Especially when you're dealing with anything you want to be accurate. Countersink is precise. All right. So this also. Really, we should give this a radius. And so the depth is from here to here, that's 46 divided by 4.5, roughly 10 millimeters, which might be a little bit too much. It is too much. Go with something I yelled at about and whatever. They should be able to do that. Then just adjust DFM back. And then this is going to be. Ooh, why does that annoy me? Inner radius is, oh, that's why. 6 plus, no, this is 14 thick, so it should be 20, yeah. Why does this upset me? Yes, that's why. I forgot to move these holes. It's at 10. This should come back. The material post the radius is not really doing anything, so we can bring this back. Okay. I think that's it. Works. Well, it works in CAD, so no evidence that it actually works. Right in CAD. It's joined. Very solid does not like that fill at all. Later. Okay. Oh, I forgot the encoder here. We have to add the encoder. I knew I was. Still, though, we can reuse this. Okay. I think that's it for today. Pick this back up tomorrow, add that encoder, and finish this out. Oh, and add some ballast back here. All right. I will see you tomorrow or next time. Within a couple.